Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, kind of the hard slot, keeping away from food. I'll try to finish on time. I guess it would have been better if our talks had been flipped around, because I'm going to talk about MDPs, but we already talked about POMDPs. So let's look at an easier model. So my talk actually has a question mark at the end, which was missing from the website, but because I'm really going to talk about work in progress. Okay, so lots of open questions which I'll be throwing up as to what is really a useful abstraction and so on and so forth. And this is joint work with Vimal, Matthew, Piyush, Kumar, and Arun, who is actually in the audience here. So towards the end of the talk, if there are questions, I'll just point my fingers to you. Right. So I'm going to start off with kind of this reinforcement learning 101, the simplest introduction to RL. So people are very familiar with the supervised, unsupervised learning and things like that. The way I always like to ask you to think about reinforcement learning is, how did you learn to cycle? Right. So that was not completely supervised or unsupervised, right? So you have to do trial and error. So you have to actually take actions and then get feedback from the environment. Right? Falling down hurts, so you try to avoid falling down and so on and so forth. Right? So reinforcement learning is essentially kind of this mathematical abstraction that captures this learning from interaction with the environment. So you sense the state in which the world is in, you take an action in response to the sensory input that you're getting, okay? And the environment changes state, go to the new state, continue taking actions, and along the way you get some kind of a scalar evaluation, okay? So I have put it as the scalar evaluation as coming from the environment, but you could think of different models for where the evaluation comes from, okay? And the goal of the learning agent is to maximize some kind of long-term measure of performance. So how long can you stay on the cycle, okay? Or how long can you avoid a collision, and so on and so forth. Some measure of long-term performance. Okay, so basically you're trying to learn a policy, which is some mapping from states to actions. Okay, and what reinforcement learning methods do is essentially specify how do you change your policy as a result of the experience that you're getting while interacting with the environment. Okay, so as already saw that this is basically the problems can be modeled as Markov decision processes, where you have a set of states, actions, and transition dynamics, which are like one-step transition dynamics, and the reward expectations. So here I'm assuming that the states are fully observable, okay? And I'm actually going to talk about a completely different class of approaches for scaling up solution methods to large problems. Okay? But therefore, to keep things simple, we'll assume that the states are completely observable. Okay, and yeah, here's a prototypical example that I'll be using just for illustrative purposes. So this is an MDP where your states are all the cells here, which you like, it's a discretized state space. Okay, and you could occupy any one of the cell at any point of time, and you know exactly where you are. Okay, and you have the actions which are like go one step in the coordinate directions. Okay, and you get a reward of +1 when you reach a state that's marked G, and 0 elsewhere. Okay, fine. I'm just zipping through these slides because we already had a pretty decent introduction to MDPs and such. Okay, so basically many of the solution approaches work with the value of a state, which is the expected long-term reward that you're going to get if you start from a particular state and continue picking actions according to a given policy. Okay, so basically the long-term, there was a pointer around which used to magically flip the slides. Okay, fine. I'll just walk and point. That's okay. So the long-term measure of reward that we are using is the discounted sum of reward, so that we don't okay, that's fine. Yeah. So the measure of long-term reward that we are using is the discounted sum, and as was mentioned earlier, it could either be interpreted as a mathematical convenience to keep the summation bounded, but also interpreted as being more far-sighted or near-sighted with respect to optimizing your rewards. Okay. So the second interpretation is kind of very popular in when you talk to psychologists and neuroscience folks who also use reinforcement learning models a lot. Okay. So where the gamma in the discount factor gamma here controls how risk averse the human being is, and so on and so forth. Okay. And we could also define something called the action value function, which essentially is the utility of picking a particular action in a given state. So it is the expected future reward that you're going to get, assuming that you pick action A in a state S, and after that you continue following policy pi. After that you pick actions according to policy pi. Okay. So except the first action, which it may or may not follow pi. Okay. So this is the action value function, and basically most popular reinforcement learning algorithms operate with the value function. Okay. Okay. So for finite MDPs, which is what I'll be talking about mostly, is that things are a little bit easier because we can talk about a partial order on the policies. Okay. And basically your goal is now to find a policy which gives you the best expected return among all classes of policies that you have. Okay. So that's basically find a policy that gives me the maximum value in each state. Okay. And it's easy to argue that there must exist such a policy pi such that you get the best possible value starting from each state and following policy pi thereafter. Okay. So we'll denote this policy by pi star. Okay. So the one thing about pi star is there could be several optimal policies in a given MDP, okay, but there is only one optimal value function at any point of time. There could be several pi's that achieve this maxima, but the maxima is always unique. Okay. So here's an example. But going back to the example, that's an optimal policy, right? This is an optimal policy. In fact, you could think of combining these to come up with many optimal policies. Many deterministic optimal policies, and of course you could mix these things stochastically and come up with a lot of probabilistic optimal policies. Okay. So this basically, any one of these is fine for me. Okay. So and then you get our familiar Bellman equation, which essentially says that the optimal value for a state should be equal to the best possible value that you can achieve by picking any action in that state, right? So it's basically max over all actions, the expected utility that you get from there. Okay, so this basically says that, okay, there's this one step utility, and after that you are doing the best you can. So this is basically the Bellman equation, and here I have just written out the expectation. Okay, so this leads to a set of system of nonlinear equations, and you could solve this in a variety of ways. Okay, so the simplest way to solve this would be to turn this into a backup equation. Okay, you start with some guess for V, okay, plug it into the right hand side, compute the max, and take that as your new guess for V star, okay, and repeat until you converge. And you can, it's pretty straightforward to show that this has a fixed point, and iterating will actually converge to the fixed point, blah blah blah. Okay, so any questions so far? I just blitzed through these first 10 slides. A, we have half hour left to go to lunch, and B, we already saw this. Okay. So similar results that you have for V star apply to Q star too. Okay, there's a huge family of solution methods. I'm not going to go into the details of those, but what I'm going to talk about is well, all of these have not too great scaling behavior, right? So when you start talking about really large state spaces, so one way to go about it is to come up with nice approximate representations and try to solve them and so on and so forth. There's another school of thought which essentially try to add structure to the policy space. Okay. So instead of saying that the policies have to pick from actions that were already given to you as part of the definition of the problem, you try to define more complex actions, try to define actions that are policy fragments themselves. Okay? And now you try to learn in the induced MDP where your actions could be these policy fragments instead of taking the original actions that were given to you in the MDP. Okay? So what do I mean by that? So you can think of a slightly larger grid world, right? And instead of planning at individual action level here, going north, south, east, and west, I could have some kind of subtasks. And you can just say, go collect an object in the room and leave the room. Okay? So that could be my subtask. Okay? So now when I learn here, it will be at the space of, okay, now go to room 1, collect the object, and come back. Go to room 2, collect the object, and come back. So in some sense, I have reduced the size of the MDP on which I am doing my learning. Okay? So of course, this assumes that I know what these subtasks are, okay, and I have the policy for these subtasks, and I can execute them on demand. Okay, and so basically, if you remember the title, it says, what are these useful subtasks? Okay, when do you say that a subtask is useful? That's basically the question that we want to ask. So what are the set of subtasks that you really need to have, okay, in order to solve a set of problems? Or can you give any guarantees on when a set of subtasks make the problem easier to solve? Okay. So the framework, the hierarchical reinforcement learning framework that we'll be using for most part it's called the options framework. It's a very almost straightforward extension of an action. So in the MDPs you have actions which have this one-step transition dynamics. Okay, an option is basically a policy fragment, okay, that takes several time steps to complete. Okay, and when an option is in execution, you will be picking policy actions according to the options policy. Okay, and so you have some states in which the option can be started, and you have some kind of a probabilistic termination condition that says that with some probability an option can terminate in a given state. Okay, so you typically have similar kinds of things in for primitive actions too in MDPs. So not all actions are applicable in all states. Okay, so if you are in a corner of a room, you really can't go in all directions and so on. So it's similar, just a generalization of the whole concept of a action. Okay. So this is a room task where there's like a building and you can go from one room to another, and depending on where I put the goal in this building, okay, my whole task structure changes, my reward structure on this task changes, my value function for this task would change, and so on and so forth, depending on where I put the goal. But I would like to define options basically that can generalize over these tasks. Intuitively these seem like good options. When you are in a room, okay, just say get out of the room, okay, or leave the room. That might be a good option to have, so that I can solve a variety of problems more efficiently, in the sense of my search space is cut down a lot. Okay, so is that a good notion of an option? Okay, so options are those that connect to bottlenecks in states. Okay, so that is one measure that people have looked at in the literature. Okay, and another measure which people have looked at is options useful subtasks are those that are useful for family of tasks. Okay, so essentially the goal is here to do transfer learning. So I learned to solve one problem, I learned something on that, so can I actually use that learning to solve a related problem? So that's basically transfer learning. And yeah, so people are talking about that, and there are other measures of goodness, but not many that have been studied in detail. But one thing to note here, all of these measures which people have looked at in the literature are mainly heuristics. Okay. So there's nothing that's really connected to the performance of the MDPs. So none of these can actually tell you, okay, if you use these options, okay, I can guarantee something about what is there in the world. Okay, well, I mean, how much more efficient it becomes to solve the problem. Okay. So there's a huge, there's a huge cottage industry, like you were talking about cottage industries earlier. There's a huge cottage industry on coming up with these kinds of heuristics for finding options, but there's really no good measure. Okay, so variety of people who directly try to find bottlenecks by analyzing various trajectories on the space. Okay, so I try to solve a number of different problems. Okay, and states or regions of the state space where I pass through, my trajectories pass through often, or bottlenecks. Okay, when I'm trying to solve a variety of problems. That's one definition which people have looked at. People have looked at forming kind of a graph out of the MDP and doing graph partitioning on that, and looked at ideas from social networks, okay, looking at what are called betweenness scores, trying to come up with this, and look at frequency of change of variables. So if a variable changes very rarely, if a state variable changes very rarely while solving problems during successful trajectories, then you should learn an option that causes the variable to change. Okay. You should learn a policy fragment that essentially causes the variable to change, and people have looked at other complex metrics, and so we looked at something which derived from dynamical systems. The idea was that we can hopefully give some kind of guarantees, but it's more work in progress, right? So before I go talk about metastability, I just wanted to make one small note here. So if you really want to make large MDPs tractable, it is not sufficient that we talk about options or talk about just policy abstractions. Okay, the policy abstractions have to go hand in hand with state abstractions. Okay, so if I'm going to talk about leaving rooms, going from room 1 to room 2, the size of the problem is not really reduced if I'm still worried about my xy coordinates in the world. Okay, so I should start representing the problem in terms of which room am I in. Okay, it's only then does the size of the problem that I'm tackling really comes down. Otherwise, it's still not a useful abstraction. So usually these kinds of temporal abstractions we are talking about, where actions that take several time steps to complete, need to go hand in hand with spatial abstractions. Okay, and so the motivation for our work is to actually, instead of trying to find what are useful temporal abstractions, look at regions of state space that are well connected. Yeah, the red does disappear. That are well connected and treat them as abstract states. Okay. So there is some text on this slide that is in red. So the red has completely vanished from the slides. And then options are now naturally defined as transitions between these abstract states. Can you go from one abstract state to the other? Okay. So that's basically. Okay. So there is this notion of metastability that's used in dynamical systems. Okay. So a metastable entity is something that is long-lived, okay, but not truly indefinitely stable. Okay. So with probability 1, as t tends to infinity, I'll leave a metastable state. Okay. So it's not a truly stable state. So if you, in physics, people think of regions of state space in which a particle is making random motions will likely to stay, okay, unless there is an external stimulus. Okay, so these regions of state space are called metastable states, and so our goal here is to identify these kinds of metastable regions, designate them as abstract states. Okay, so could be states connected by bottlenecks. You can immediately see that if I'm doing a random walk in a room, the probability that I'll leave the room is very small. With a very high probability I'll be within the room, because I have only one doorway through which I can leave the room. Okay, so the probability of me staying in the room is very high. Okay, so people solve this. The usual solution method from dynamical system literature is called the Perron cluster problem. So the goal is to find the discrete invariant measure of the stochastic matrix corresponding to random walk on the underlying system, right? And so for uncoupled system, okay, you can talk about a discrete invariant measure, but those are not very interesting for problem solving perspective, right? So if you have rooms world, it's really not uncoupled, but they are nearly uncoupled systems. Okay, so the problems that have interesting structure for which we can find useful abstractions are nearly uncoupled systems. And so you basically end up trying to find what we call almost invariant measures. Okay. And the goal is now to find what is an almost characteristic function which kind of assigns a degree of membership for each state to one of the invariant sets that you come up with when you are analyzing the stochastic matrix. Okay. So if that doesn't make too much sense, maybe this would. So if you think of a fully uncoupled system corresponding to each connected component of your state space, okay, you will have one invariant set. Okay. And if you think of projecting your states onto these invariant sets, onto the characteristic function for the invariant set, you will essentially get just these corners of a simplex corresponding to the number of the dimension of the simplex corresponding to the number of states underlying the thing. Okay. But now, since we are considering almost characteristic functions and looking at first order perturbations, so you basically get a rotation on the simplex, and the goal is to find a characteristic function such that the memberships it assigns minimizes the deviation from this almost characteristic function. Okay. And so PCCA plus is kind of the reigning champ in solving the Perron cluster problem. And so we basically use PCCA plus as a black box, but the problem it is solving is trying to assign the characteristic function so that it minimizes the deviation from the rotated simplex structure. Okay. So there are a couple of nice things about PCCA plus. So if you notice that we are not really trying to add any kind of regularization in terms of the stable regions that are produced. So what do I mean by that? So if you look at typical spectral clustering methods, they have to have some kind of regularization that is added in order to make sure that you don't get really small clusters, or the problem is well defined, and so on and so forth. So looking at some examples here. So this is a domain which is kind of like a room within a room, kind of like a box within a box kind of a setting. And if you run a very naive spectral clustering algorithm on it, it basically tries to split it into two equal clusters. Okay, and you could run some kind of normalized cut algorithms on it, which give better results, but not always, right? So sometimes it just messes up the connectivity structure in the world, mainly because it's the regularizer it adds to, it doesn't really respect the dynamics of the transition that's happening in the underlying world, right? And we could do things like split really tiny parts of the state space into a different abstract region, and so on and so forth. This is more like an empirical validation of what is going on. And more interestingly, for the RL community, so we could do things like model presence of objects in the world which change the dynamics, which is not typically something that was done earlier with all the other earlier works that had looked at option generation or automatically generating temporal abstractions. Okay, so there is an object in this world, some kind of a key that you need to pick up. Okay. And when the agent is navigating around the world, when it picks up the key, that's a substantial change in what the agent can do. There's a set of states which are accessible to the agent now, which were not accessible earlier. So in some sense, in a behavioral way, it's really a bottleneck. Okay, it's maybe not in a structural way, but in a behavioral sense, that's a bottleneck. And PCCA plus actually figures that out, and it says that okay, so it splits the world into two clusters, okay, 1 and 2, and so this is the membership for the states in cluster 1 when I don't have the object. Okay, so and this is the membership for states when I have the object in cluster 1. So basically, all the states in cluster 1 are states when I have the object. All the states in cluster 2 are the states when I don't have the object. And now the option that I have to pick up, option that I have to learn, is to go pick up the object. So we have run this on more complicated worlds, and you actually get options that are very close to what a human would actually craft as options in those worlds, and way better than what automatic option generation methods get us, existing methods get us. Okay, and another thing about having this characteristic function is that it also allows us to derive a policy for executing this option. So if you look at it, So when I'm without the object, okay. So if in some sense if I follow the gradient of my okay, without the object, okay. If I follow the gradient of my characteristic function, okay, for the other cluster, so I'll actually have a policy that will tell me how to go and pick up the object. Okay. So when I'm very far away from picking up the object, I'm going to have a very small membership for the cluster in which I have the object. So basically I just follow the gradient of that membership function. I'll go to the part of the state space where I actually have the object. Okay, so because I have this characteristic function, it also gives me a way of defining the policy that allows me to go from one abstract state to another. So I don't really have to do any additional learning for the option policy. Okay, and of course this is just to beat up on bottleneck state algorithms. So typical bottleneck algorithms would say that, okay, start from here and you go here. So whichever doorway you pass through will be identified as the option or the bottleneck space. Okay, but in reality, you have one connected component that is outside and another connected component that's inside. So we can do this kind of, I mean, this is true of any kind of clustering algorithm, so which will essentially find these connected regions and not just bottlenecks in state space. Okay. So yeah, so we did this, and it turns out that we are getting very useful options in terms of modeling the world and also in terms of efficiency in learning, etc., etc. But I'll skip that slide. But another interesting question that we wanted to ask was, okay, we are doing all this careful analysis of the structure of the world, but in the end of the day, what we are really trying to do is increase the connectivity between the states, right? So we're taking almost uncoupled systems and trying to make them more coupled, or whatever be the motivation, but we are essentially increasing connectivity in the world. So can we do something in some sense dumber, you know, we not really worry about the connectivity, the structure of the world, but do something more random. You know? So we looked at ideas from small world networks. So people talk about navigating on small world networks. Okay, and so basically the fact that if you do distributed navigation in a network that has just a small world, you can basically reach from any point to any other point in order log n squared, where n is the size of the graph, size of the network on which you are navigating. Right. So the idea was now to see that if we can choose our options so that we can convert the existing MDP into a small world. So for people who are not familiar with small worlds, I mean, so you must have heard of the phrase that it's a small world, right? It came out of this experiment in the 60s by Stanley Milgram, where he basically said, he gave a bunch of letters to people in the Midwest and told them to mail it to a stockbroker in Boston. Okay. And he told them that you can only send it to people who you know on a first name basis. Okay. And so of the letters that made it to Boston, okay, the average number of hops it took was only 6. Okay. And repeatedly people have shown that in many large real world networks, there is always this small diameter property. And not only is there the small diameter property, but people are able to find pretty short paths, maybe not the shortest paths, but pretty short paths with only local information, okay, not necessarily knowing the complete adjacency structure of the network. Okay. So Kleinberg came up with this key insight that if the long range connection, so you have some amount of people who you know, so your neighborhood, okay, and then you could have a long range connection. So if across the network, if your long range connections are distributed as an inverse power law, okay. So in the sense that the probability that I'll have a connection with somebody who is d hops away is 1 by d squared. Okay. So if it is distributed as an inverse power law, then the resulting network will have a distributed navigation property. Okay. That's a pretty, and only then actually, that's a pretty powerful result. So then and only then will the resulting network have a distributed navigation property, and that depends on the dimensionality of the underlying lattice and so on and so forth, right? So the intuition here, I mean, so you're basically inserting edges. So this is you start off with a regular lattice, okay, and you insert edges that are proportional to 1 over d squared, okay. And the basic intuition is that suppose you want to reach any point in this lattice, so you start looking at increasingly larger neighborhoods, okay, exponentially larger neighborhoods around that point. And because of the way you are distributing these edges, there is always an edge that will take you from a neighborhood of size j to a neighborhood of size j minus 1 with probability 1. There will be an edge that takes you from neighborhood of j, neighborhood of size j minus 1, and there are that's because there are 2 power j nodes in the neighborhood of size j, okay, and you have a probability of 1 by 2 power j of actually finding an edge to the next level. Therefore, you can actually hop from anywhere in the graph to your goal, okay, in log n the whole squared steps. So this is basic motivation. This is a basic intuition behind the proof. Of course, you can be more formal, but I'll not do that here. So traditionally we use these kinds of bottlenecks or doorways and so on and so forth. But now what we do is we sample from this inverse power law distribution, and so basically we are going to get a lot of these kinds of random options. Just take a jump in space somewhere, okay. And yes, so how do we measure the distance in the space? Is it measured as lattice distance, or is it measured as the distance in the difference in the value function? So value function would induce a norm. Okay, is it measured as the distance in the according to the value function? It turns out that, so we don't really have to worry about it because of the way the value function is computed. So we can also show that it's always bounded by, slightly bounded by the actual distance in the state space. Okay. And so there are many practical questions you have to address. So the thing is, there are many options that are required. How do you efficiently learn them? And so one of the things which we do is that we restrict the number of long range links you're going to get to 1 per state. So you're really not blowing up the search space. Okay, so every long range action is applicable only in one state. Okay, so when you come to a particular state, your branching factor would actually effectively go up only by 1. Okay, so it's not like even though I might add like a few hundred new options to my problem, I'm not blowing up the search space. Okay, and second thing is, given that there are so many options, how do you learn the policies? Okay, so if you remember, the guarantee that we need is that there is an option that takes you exponentially far away. Yeah, that takes you exponentially far away, and so it doesn't necessarily have to go to a particular point in the space. It could just go to somewhere to a region in the space, and therefore we don't really have to be exact in learning the option. So it could be very inaccurate. It could have some kind of some kind of cheap learning mechanisms can be used. Okay, so the basic algorithm is that I'm going to train an agent on some set of tasks which are performed in the same domain. Okay, and for each task, okay, I'm going to look at the path that I found, which is I'm going to find the optimal path, and then basically sample a fragment of the optimal path and save that as a option, right? And so it really does not require us to know the MDP, which all the spectral methods needed to know, the betweenness methods needed to know, and we don't need to build a model, and we don't need to learn policies separately, and so on and so forth. There are lots of interesting things. We're really not doing anything clever here, right? And I'll skip the algorithm. So, but the nice thing is, at the end of the day, we can actually show that treating the MDP as a graph. Okay, treating the MDP as a graph where the states or the nodes, and there is an edge if there is a action that takes you from one state to another. Treating the MDP as a graph, if we can show that if there is a function f that respects the lattice distance, so basically that's bounded by the lattice distance, like the value function is, which is what we want, right? And if G contains long distance edges, okay, distributed according to our inverse square law, then an epsilon greedy walk on this graph, okay, will only take order of log v squared steps to reach the global optima in F. Okay. So basically it gives us some existence guarantees on efficient solutions for MDPs, and there is no such guarantees that have been provided for any of the other optional learning mechanisms so far, and this is the first theoretical results on achieving this kind of effectiveness. So yeah, so we can show that we do better than well, not having any options at all, or having a lot of random options, or using betweenness scores, which seems to be currently the best mechanism for generating options. And then using our small world options. So basically this is a cumulative reward that you are getting over all the episodes. So basically as the slope keeps changing, that means you are learning better. Okay. So the best performing curve is obviously when we add betweenness and small world. So throw in everything together, so we get really good good results. But then just the small world options alone does better than any of the other challenges that we have. Okay, and we did this on a variety of problems. We got better results, and we also asked another question. So we have a significantly more number of of these small world options, right? So we added like 200 small world options to the problem, while the betweenness options were a lot fewer. Okay, in some cases there are only 4 betweenness options, some cases 8. So are we being fair in comparing betweenness versus small world options? Okay. Are we actually spending the same amount of effort in learning those? And so what we did was we just basically started budgeting the learning. So you can learn option policies only for certain number of epochs. Okay, and and lo and behold, what happened? So the betweenness options, which really required you to reach a particular point in space, a state of high betweenness, okay, which really required you to reach that point in space. So you really couldn't learn those policies with a small number of epochs. Okay, so the performance was actually bad. You can see that the slope hasn't turned around at all for the budget limited betweenness learners. While the small world options, because they could operate with even inaccurate policies, you did not even reach to the goal that you are aiming for. As long as you are somewhere in the vicinity, it is fine. Okay, so the small world options were doing much better even on a budget, and that is one budgeted version of the small world option, that is the optimal betweenness option. So we're almost at optimal performance even when learning on a budget. And of course this is the optimal, this is the curve reproduced from the previous graph. Okay, so the takeaway here is a new option generation scheme, okay, and it can give you theoretical guarantees on existence of solutions, and on performance wise also it's competitive on standard domains. And so this is the big question. So small worlds are competitive. Okay, this is basically I inserted things at random. So are we missing something? When people are looking at all these other ways in which they can insert options, but they are not able to give any kind of guarantees on what is happening. And so yeah, this detailed structural analysis really needed to improve performance, and behavioral criteria that can be used and things like that. So basically there's no well formulated optimization question that people ask when they are looking at option learning. So that's one of the things that we have been looking at. So any questions? So if you have any. Sure.
That may be a dumb one. So I was thinking betweenness is more like a hard constraint and this small world is more like a soft constraint. So
Yeah.
can there be cases where in the soft world assumption, small world assumption, you kind of diverge away from the solution?
See, that's the whole thing, right? So as long as I am somewhere close to the intended target, as far as my small world transition is concerned, I am happy. The guarantees that I need for my theorem will actually hold. So as long as I am somewhere close in space to that. So
Can there be
See, the point is when we actually sample these trajectories to include to this, include in our set, we actually throw away trajectories which lead us to worse states. So whatever we retain in the set of options are trajectories that actually move us towards some goal in some task that we have solved in the past. Okay, so that particular option might actually be taking you away from a different goal. For example, in the rooms world, right? If suppose I'm going to room 1 and I have an option that takes me to room 2, that will obviously take me away from my goal. But it's just that during the learning process, you learn not to pick that option. That's basically that's how it will get put out. I'm not sure I got your question completely, but.